thiols and sulfides are the sulfur analogs of alcohols. So if that were oxygen instead of sulfur, that would be an alcohol. And sulfides, the sulfur equivalent of an ether. And then I'm going to throw in one more here. Disulfides. These are important in biological reactivity. Disulfides, that sulfur-sulfur bond is significantly stronger than the oxygen-oxygen bond. It doesn't cleave so readily, and disulfide bridges are important secondary features in protein structures to give us the three-dimensional structure of proteins and biomolecules in general. Okay, so first, how do we make a thiol? General reaction here is we take an alkyl halide plus hydrogen sulfide that has been deprotonated, so this is the thiol equivalent of hydroxide. This is a classic SN2 reaction, so it has all the limitations in R groups that SN2 reactions have. It does a simple displacement reaction to produce the thiol product in this reaction. So, as an example, benzyl bromide plus the anion yields the thiol. So that's how we can make them. Now, this anion comes from H2S. Now, water, as we all know, is not very smelly, but H2S is the characteristic odor of rotten eggs. And that's not so great. We don't want the lab stinking like that. So there's an alternative. We can react an alkyl halide first with something that's not volatile but contains the sulfur. And in this case, it's going to be thiourea. Now, urea, where that sulfur is an oxygen, is a standard byproduct of metabolism in animals. But we want the sulfur analog of this. And so thiourea is not volatile, so it does not produce that odor. We react these together. The sulfur is still very nucleophilic and does a classic SN2 type reaction. And then we treat that with sodium hydroxide to cleave and hydrolyze this thiourea, and we get from that the thiol product. So there are some specific examples there for you. I'm going to leave it for you to go and take a look at those. I'm not going to work them out here in detail because I want to get to the next aspect of this, which is the oxidation chemistry of thiols. This is important in biological functions. Thiol, there's a whole class of amino acids, of course, that have sulfur in them. And so these, both thiols and sulfides, and of course the thiols, can make the disulfide bridge. So how do we get to the disulfide? Okay. The disulfide comes from reacting two thiols. So we need two of these. And again, if they could be side chains on a protein that might be a number of amino acids apart, but they come around to get close to each other, and you make that sulfur-sulfur bond, and this is where These are very important. So the standard reaction here is we use iodine, zinc, and acid, and we oxidize the sulfur and we reduce the iodine because we're losing a sulfur hydrogen bond. Okay, we lose that, so we're removing hydrogen, so that's an oxidation process. So, simple case here, we can take benzene thiol under those standard conditions, and we produce that product. Okay. All right, now let's move on and continue in this section with sulfides. Okay, so sulfides. Again, these are made in a very straightforward manner. We can take the sulfide anion. And then we could have made that by deprotonation or putting in a reactive metal like sodium or potassium. And we react that with an alkyl halide. R can be the same or different. I'm not going to make that distinction here. And again, this is a classic SN2 substitution, so it has all the limitations in the alkyl halide that we would have for any other SN2 reaction. Again, I'm not going to reiterate all of those here. Go back and review them if you need to. This produces the sulfide. Now, low molecular weight ones are, again, smelly, stinky compounds. In fact, ethane thiol is the characteristic odor of natural gas. Well, is it? Actually, it's not. Natural gas is odorless, but it wouldn't be good to have a leak of natural gas and not know about it. So at a part per million or so, they add ethane thiol, and it's so smelly that we can detect even the slightest trace of a natural gas leak. So these are important uses for this as well. Now, sulfides, what can we do with them? It turns out that one of the things that's very interesting here is that they can be sequentially oxidized. And it depends on the oxidizing power of the reagent you use. So hydrogen peroxide, might have it under the sink in your bathroom, a very dilute 3% solution of that. It's a good mouthwash to kill bacteria and things in your mouth, or turns out, according to dentistry, it's really great for killing COVID in the oral cavity. So we have hydrogen peroxide. It will oxidize the sulfur one time. So sulfur here has two lone pairs, and sulfur is not on that second row where oxygen and nitrogen and carbon all are. So it can have an expanded octet. And so we can oxidize this, and typically it's drawn with a double bond there. And that sulfur still has another lone pair that is actually chemically active. So you'll typically see that drawn with the double bond, but this is the equivalent of this sort of dative bond representation. And then we don't use dative bonds very much, but this is one place where it's very useful, because the sulfur is very positive and the oxygen is very negative here. And we're spending a lot of time on this because there's a very common solvent, DMSO. It's used all throughout organic chemistry. It's used as a denaturant in protein chemistry and other things in biology. Again, a very good polar aprotic solvent, dimethyl sulfoxide. So these are sulfoxides. So hydrogen peroxide has sufficient oxidizing power to convert a sulfide to a sulfoxide. Now we can go further to the sulfone. So we oxidized one of the lone pairs, right? Here's our dative bond form, and produce a sulfur with 2 oxygens. Now again, you typically see this drawn with this expanded octet, if you will, at sulfur. This is the sulfone. But we need a stronger acid, and in fact what we need here is a per acid, something that's much better than hydrogen peroxide at transferring an oxygen atom. And remember, we just used per acids to transfer an oxygen to a double bond. That was epoxidation. So if we can oxidize a double bond, we can certainly oxidize sulfur with these. And so MCPBA would be a classic example of a per acid that we would use there, but almost any of them will work. This is just one that's convenient and readily available to use in a synthetic laboratory. Okay, so that's oxidation. One last reaction of these, I'm going to see if I can squeeze it in over here. These lone pairs on sulfur, sulfur because it's more polarizable and because it's larger is much more nucleophilic than oxygen, and so this will readily alkylate. So for instance, we could add methyl iodide to this, and in again a classic SN2 type reaction, you alkylate one of those lone pairs. So these are the chemistries of sulfur that are very important for us when we get to biomolecules.